So this is again called linear indexing. So far, what have we done? For each dimension, we have used the coordinate x0 to xd minus 1, d being the space dimension, and each one holds L binary digits. So the total information is d times L bits, which is L if L is 20 or 30, is 60 or 90 in 3 dimensions. So we could, of course, create a total numbering of these elements and just indexing by a number with, between 0 and dl exclusive. So let's do that. As I said, we will count the children in order of their child ID and do this recursively. So at any given intermediate level, little l, which is anywhere between 0 and big L inclusive, we have only L bits of information in this coordinate, in each coordinate, which we call significant. So of all the big L bits, the leftmost big L, the leftmost L are significant and the rightmost big L minus L. So my right, your left, right? My left, your right, and my right, your left. So the my left L bits are significant and the my left big L minus little l bits are 0, which they have to be for any valid element. Remember the definition of the is valid algorithm. So on some level we have a count of d times little l. We would construct this number recursively by the following definition. We have a function that we call linear ID, and at the root we just call it 0. And then each child of the root, in 3D they are between 0 and 7, we would give them the linear ID of the parent, but shifted to the left by d bits, and add the child ID, which means we are moving the linear ID of the previous element of the ancestor to the left, freeing up 0 bits on the right, and those 0 bits we are replacing with 1 bits depending on the bits in J. So J again comes in as a bitwise information, 1 bit per dimension. So you see the formula here. It makes sense, I hope. So this is an inductive definition. We see immediately that for some little l that is not 0, the linear ID is in the expected range of values between 0 and dl, which can be proven very easily by induction from that definition there. So as a bit of a note or a reminder, we will only allow our algorithms on valid input elements, except is valid, of course, which we can call on anything, and it will tell us if this element is valid. And we will assume that we only call algorithms on legal parameters, such as the child ID or a sibling ID or some target level L prime. In the computer code that we'll be writing, of course, we must think of the fact that somebody will call the functions inappropriately. So it is our responsibility at the beginning of every function to ensure that we are called legally and otherwise exit out of the function with some well-defined error code. We also must guarantee that once we proceed with our function and finish with it, that our result is valid in our sense. So we need to evaluate preconditions to guard against improper calling and postconditions to verify that our code is okay. That's something we have to do in practice, but here for mathematical purposes we will skip that. So we had property 3.6, where we said that each child and child of child recursively automatically gives us a valid element. What about the converse? That, or not the converse, the reverse direction of the conclusion, that we could ask, is any valid element derived from the root by a certain number of child calls? And the answer is yes. So there is a bijection between well, bijection is the wrong word in this context. But we can go from the root to any valid element by child calls, and we could also figure out this sequence of child calls from the valid element itself. So the formula you see here, 3.2.3, tells us exactly that. For each level little l, we have one child call to derive it recursively from the root. So I have L calls of child, and the child ID is a number that I call j big L minus 1 all the way down to j big L minus L. So we have little l different child numbers that correspond to the little l different calls of child, and we apply this whole thing to the root in the beginning. We can say furthermore that the numbers j here from big L to any L prime between 0 and little l, between 1 and little l, are unique. So how would we prove this? Well, we have to prove this separately for all levels. We can begin with level 0, where it is trivial, is valid, inspected for level 0 element means that big L bits of all coordinates have to be 0, but those are all bits. So we automatically enforce 0 coordinates, which is identically to specifying the root. For any bigger levels, we can go by induction, and we just have to say that we have some element that is valid as a general assumption of our property, and all we have to say that it can be derived uniquely from its parent, since for the parent we have the previous level, the induction assumption. So suppose we have a valid element on level little l, we can examine the first significant bit from the right, which is j big L minus little l here. And this we can basically, the bits are here. We know that they are either 0 or 1, unspecified. By validity, all the bits to my right of that are 0, and all the bits to my left of that are also anything as far as we know. The bits to the right are 0 due to the is valid assumption. And then we take the first significant bit from the right that is not 0, add it up by dimension to get this number, which is between 0 and 2 to the power of d, which gives us this j. And then we can construct another element p by just taking the same coordinates and zeroing out all the significant bits, but for the next higher level, little l minus 1. So the bits we have identified in 3.2.4 are removed from the axis and we get p. So p has some bits even to the left of that, and that construction of p naturally gives us a valid element by just inspecting the isValid function. So p is valid by the induction assumption. We know it is the child of a child and so on of the root. And now we only have to compare the child call of p with the number j big L minus l, which we can always do as long as L minus 1 is not big L, but that is clear from our construction here. And we see that it is always the same thing. So x and L is by definition of the child function, and p the j L minus little l child of p. So in one go we have proved the conclusion and we have proved uniqueness, since for any other j that is not j big L minus little l, we get a sibling of xl and not xl itself, which means there's really only this one L, and this holds inductively. So the sequence of j's is unique, which finishes the proof. This is actually quite easy to do. So validity is equivalent to an element being a child and a child so on of the root with well-defined numbers. Those numbers are always a child ID, as you could see in the proof. Let me write this down explicitly. So j big L minus little l prime is always the child ID of that respective branch of the tree, depending on how high we are in the induction. So the ancestor of the original element at some equal or higher level, higher level meaning lower L prime, so it's a smaller little L prime, which is higher up the tree if the root is at the top. And then this holds for any L prime, and so we can construct this number for all the L primes from 1 to little l, which means we have a whole bunch of child IDs. So let me keep that in mind for a second. We have a different formula here. We could, of course, reverse the child formula from earlier out of the definition of the linear ID to apply it to a parent, and we see that we can derive it from the element of the from linear ID of the element itself, and you see that L greater 0 is not the right precondition here. We would have to say L. No, this is actually right? So in order for the parent to exist, we need little l to be greater than 0, because the root has no parent. And then we get the linear ID of the parent by narrowing down the range by a factor of 2 to the power of d, and that's all we have to do. We just round down, and then we're there. But to continue our argument, we have seen that linear ID is just a concatenation of the child IDs and of course we could understand this as a big L digit number where each digit is in base 2 to the power of d. So in 3 dimensions we have an octal number with big L octal digits. So again, here you have it. The linear ID is just concatenating the child IDs in binary, or if you understand each child ID as one digit of the 2 to the power of d base, then this is not in binary but in base 2 to the power of d. You see also that we have little l entries here, depending on the level of the input. So let me write this down again. Equivalently, we can of course just explicitly spell out the child IDs. Importantly, we begin with the first element below the root, up the branch from XL, the second element below the root, and so on. The ancestor of the same level is the element itself. The ancestor one level higher is the parent, otherwise we just call ancestor generic. And if we remind ourselves that the bits in the child ID are separate in meaning by dimension, we see that each child ID octet has a z number, a y number, and an x number, and this holds for every other child ID as well. So we have z, y, x for the one child ID, then we have z, y, x for the other. So we see that the bits in the linear ID are just interleaved coordinate bits from x0, x1, and x2 up to x d minus 1. Which is actually a concept that we had put down in 1.4.1, so please look at that formula and you will recognize immediately what we're doing. To map the range into the maximum level, we could just left shift by big L minus little l bits, filling up the right with zeros, and this is something we would call big I of XL, so it's a linear ID, but not of X. We take the first descendant of X at the highest level, big L here. It turns out this number only depends on X and no longer on little l, which you can easily verify. We also write this since I of X is really just a permutation of bits. It is unrelated to the validity of X for any chosen level of inspection, little l. So I suggest that you take a couple elements that you just put down on paper, you write down x, y, and z in binary, and then you compute the linear ID, write that down in binary, and find the correspondence of the bits between the two representations, or equivalently, the permutation over d times big L, many items. You could actually prove that there's a bijection here between linear ID and the coordinates of a valid element given a certain level. New functions. So we understood linear ID. We can define the successor as being the linear ID plus 1, but then of course we don't want the number, we want the x and L pair, so we have to take the inverse function on that linear ID with respect to that level, I must say. So I should parameterize linear ID inverse really with L, otherwise this is not complete, very strictly speaking. This works as long as we're not the last element in the tree, the top right corner. The top right corner would be the last descendant of the root at that level. So as long as this is not equal to XL, we can call this function. Similarly, if XL is not the lower left corner, which would be the first descendant of the root, then we can just decrement the linear ID by 1. Of course, we have to do 2 of those permutations, big I and big I inverse, and that is overly expensive in practice, especially since we have to write a loop over all the levels little l. So we could replace this by a recursion that is actually quite spiffy here. So successor of XL, what would this be? Let's do the easy part. We could just take the sibling of XL, but with the child ID incremented by 1. So that's a very easy function to call. But what if j, the child ID, is already the maximum of 2 to the power of d minus 1, this one here? Then sibling is not legal to call. So what can we do? We can go up to the parent, take the successor of the parent, and the first child of that parent. So we would take the parent, XL here. The parentheses here are not close to scanning, sorry. So you take the parent, then we take the successor, and then we take the first descendant of the result at the level L. So we get a result at the same level as X, which is what we want. So this is the successor. You can try to prove, please, if this is actually the identical function to the successor up here, so that would be one exercise. You can also take the predecessor function here. So successor would be here and there. Predecessor, you could try to write a function similar to this one, but for predecessor. So that would be an exercise that I really recommend everybody doing. I have another example as well that is in the notes. If you take page 40 from the repository, you will see another example about the bijection between the x coordinate and the sequence number, the linear ID, with respect to the leaves of the tree.